In this module, we introduce the kinetic theory of gases and explain its basic assumptions. Now we will advance our understanding of the microscopic perspective of matter by considering the translational motion of gas particles. The foundation for this development is a theoretical framework called the kinetic theory of gases, also known as the kinetic molecular theory. The kinetic theory of gases relates observable properties of gases, such as pressure and temperature, to the motion of individual gas particles. This framework is one of the most remarkable models in physical chemistry because it derives powerful quantitative results from just a few simple assumptions. It also provides the foundation for more complex topics such as collision theory and reaction dynamics. The development of the kinetic theory of gases starts from several key assumptions that simplify the description of a gas at the microscopic level. First, a gas consists of a large number of individual particles, atoms or molecules. Second, the total volume of all particles is negligible compared to the total volume occupied by the gas phase. In the kinetic theory of gases, the particles are treated as point masses or as tiny spheres with mass m, whose own volume is much smaller than the average volume per particle in the gas phase. The only form of energy considered in the model is translational kinetic energy. This is the energy associated with the motion of a particle as a whole. Rotational and vibrational contributions, as well as potential energy from intermolecular interactions, are neglected in the simplest form of the theory. The particles are permanently in a random motion. This phenomenon is known as Brownian motion. It arises because the velocities of gas particles are continuously changing due to collisions. There are no intermolecular forces acting between the particles except during brief collisions. This means that particles travel in straight lines between collisions and do not attract or repel each other in any other way. The motion of particles obeys the laws of classical mechanics, specifically Newton's laws. The motion of particles is continuous and deterministic between collisions. When collisions occur either between particles or between a particle and the wall of the container, they are perfectly elastic. The total translational kinetic energy of the colliding particles is conserved. There is no energy loss due to deformation, friction, or internal excitation. These assumptions define the kinetic model of an ideal gas and allow us to apply classical mechanics to describe the behavior of gas particles. The assumptions are valid when the gas is dilute, meaning that the average distance between particles is much larger than their size, and when the temperature is not too low so that quantum effects can be neglected. Under these conditions, the kinetic theory provides a powerful framework for linking the microscopic motion of particles to macroscopic gas properties.